Hello, this is for anybody that might have either missed the notes because you weren't here on Monday, or if you want to review longitude, latitude, and longitude. This is what I'm showing in class on Monday. So we're going to talk about latitude and longitude and try and answer some of the questions that people have. So first, many people wondered how they could remember latitude and longitude, and I remember it by a ladder. Uh, the ladder, the longest parts of the ladder, these parts right here, are the longitude. So the longest parts of the ladder are the longitude. They go up the sides. And then the rungs would be what's left, the latitude. If you can remember it another way, great. Latitude measures angular degrees north or south of the equator. So if I slice the Earth in half from through the North and South Pole, we'll see this inside of the Earth. And if I take this center point of the Earth and I draw a line, that's the equator, and whatever that angle is, that's your latitude. So latitudes are really just a measurement of where you are in terms of your angle relative to the equator. And if I were at the North Pole and I drew, this is as if I took the Earth and I'm looking at half of it, the inside half. If I take that point at the equator and I go up to the North Pole, that angle is a 90-degree angle. And so the North Pole's latitude is 90 degrees. And South Pole latitude is 90 degrees. That's why your maximum latitude or on the Earth is 90 degrees. Because once you get beyond that, then you're back to whatever the lower latitudes would be. So that's your maximum. The one thing that we can use to help us is Polaris, and Polaris is really critical in being able to identify your latitude if you don't have a map or you don't have GPS on you. And if you look here, if you were to take a line that goes through the North Pole, down through the South Pole, and that we call the axis of rotation, the Earth spins around that point. If you were to draw an arrow to that, it would almost point directly to the Polaris, to a star. And that star is the North Star, or Polaris. And to find it, you have to go outside, find the Big Dipper. You have to kind of know in general where the north is to help you with this. But if you spent some time looking, you would be able to find it, find the Big Dipper, and the bottom two stars point almost directly to a star. And that next brightest star that they point to is Polaris. If you were to stay out all night long and have a camera running, this is what you would see. You would see these stars arcing across the sky. And the central point here is Polaris. And this star does look like it's moving a little bit, and that's because it's not perfectly above the North Pole, but basically all the other stars appear to revolve around that one star. So as we're rotating on our axis, it's causing us to see these stars spinning in a circle in the night around Polaris. And one of the things that we have to think about is this altitude. So when I say altitude, this is what I mean. I mean, if you were staring outside looking at the horizon, here's the horizon is where the sky meets the ground. And if I point to an object in the sky like the sun or a star, however high that is, whatever angle that makes, that is its altitude in degrees. And if we go back to Polaris, when you stand outside and you point at the horizon and then point up to Polaris, you should get an angle. And that angle is equal to your latitude. So we can use that to our advantage. We can use that to help us figure out where we are. So if we're at the North Pole, here's the horizon. If you were to point up to the North Star, Polaris, it would be up here. Sorry about this. All these rays are moving straight down, and so you would have a 90-degree angle, and you're at 90 degrees north latitude. Now this you have to kind of imagine that I can turn this, turn the whole screen, rotate it, because this is the horizon. This is if you're standing on the Earth here at the equator, this is where you would be standing like this. This way would be up. That would be the down to the Earth. The horizon would be straight out ahead of us, and Polaris would be coming in straight ahead of us. And so it would be at the horizon. It would be at 0 degrees above the horizon. It would be right at the horizon. So your latitude is 0. And so as you move from the equator north, Polaris starts to rise. Here's the horizon again. We're at about 50 degrees, and that's at about a 50-degree angle. And as I go to the North Pole, as I go to the North Pole, what happens to the angle? It increases to 90 degrees. So as you travel north, your altitude of Polaris changes. It rises in the sky. It goes up in the sky. If you stay at the same latitude, Polaris is going to stay at the same latitude. So if you go out tonight and you're at 50 degrees north, it's going to be 50 degrees above the horizon, and tomorrow night it'll be 50 degrees above the horizon, and the next night, and the next night, forever. If you go someplace else that's also at 50 degrees, then they will see Polaris at the same spot. They'll see Polaris at the same place as you. All right. Now, longitude, we measure, if I were to slice the Earth in half going across this way, at the equator, we would see that here's the prime meridian that goes through Greenwich, England, and we can mark off 15-degree intervals to go around and find our lines of longitude. Now, time zones are critical. Longitude is critical for time zones. If we are going around the Earth and we look at a globe, it takes 360 degrees to go all the way around it, and we spin once in a day. So that's 24 hours. So if we take 24 hours and we divide it by, if we take 360 degrees and we divide it by 24 hours, we get 15 degrees per hour. So if you take 360 divided by 24, you'll get 15. So that means that for every hour, the Earth spins 15 degrees. So if the prime meridian were here in an hour, the Earth will spin this way, and now the 15 degrees longitude west, 15 degrees west, will be at this spot as it spins around. So if we think about days to keep time working correctly, and so that we're not all everybody's not at the exact same time, we divide the Earth into 24 separate time zones, one for each hour of the day. So there's 24 time zones, and they're 15 degrees apart because it takes 15 degrees to move every hour. So here's Z time, Zulu time. They use that as a universal time because it's a way for everybody to be able to set their watch. So if you want to talk to somebody in a different country, you might set your time based on Zulu time. Or the United States military is all over the world, and they use Zulu time so that they know when to coordinate certain airstrikes or to movement of planes or movement of ships. So we use Zulu time for weather, they use it for the military, and that's the time right here at Greenwich, England, right along the prime meridian. If we move to the United States, we see that we have 4 time zones: Eastern time, Central, Mountain, and Pacific. And if you go west, your time will be less. So if it's 8 o'clock here in Eastern time, it'll be 7 o'clock in Central, 6 and 5 in Pacific. If you go east, your time will increase. So if it's 5 a.m. here, it'll be 6 a.m., 7 a.m., 8 a.m. So depending on which way you go, that determines whether you're gaining time or losing time. Okay. How many time zones, or what's the time difference between Zulu time here in England, and Eastern time? Well, let's figure it out. If each one of these is an hour, that would be 1 hour behind, 2 hours, 3 hours, 4 hours, 5 hours behind. So there's 5 hours of difference between those 2 time zones. And we can use that to our advantage when we're looking at how to determine longitude from our time. And we'll do that on Tuesday. I hope that made sense. And if you have any questions, please let me know.